Was 30 on the student sister.
Hmm. Hmm.
My can't drive. I was on the phone with my sister.
Mhm.
She's on phone with her. It's a good job. But we're just don't have no. But yes, yeah. Just like they're talking to us.
C like the.
All right, everybody, I think I'm gonna go ahead and get started, and hello and welcome. Time change, all right. It now means that every clock in this building is off by an hour. So it says it's 3 o'clock, but it's 4 o'clock. Anyway, it'll take them, they'll get them fixed up just about a couple weeks before they have to turn them back again. They'll have them all corrected, but anyway, I hope that that didn't throw you guys off too much. I always miss that hour of sleep, but then on the other hand, I love having it lighter outside later in the day. This is actually my time of year that we're moving into here. So hopefully you guys will enjoy it as well. Let's see, a few announcements that I want to make here. First of all, I want to thank all of you for watching the extra credit video. I just checked right before class and it looked like basically everybody did it, which is super. So you all get that extra credit and that'll mean you're hopefully ready to go for what we're going to talk about later on in today's class. But before we get to that, just a couple of other things. There's actually nothing due tonight. I figured this out strategically. It was originally, I originally was going to have you turn in homework number 14, which is on section 6.1. I was going to have you turn it in tonight. And I realized that I was going to wake up this morning in Seattle, which I did at 3 o'clock in the morning, and went to the airport. And so I've been up already for 12 hours. And I'm going to now teach for 4 hours. That'll be 16. Then I have all this whole office hour thing tonight, which I am going to have. However, if you would like me to be coherent for answering your questions during office hours, I would not wait until 11:30 to come into Zoom when I'm like practically ready to shut off the lights. So my advice would be, if you got some questions for me today, try to stop by on the earlier side of my office hours, like around 8 would be super. There is nothing actually due today, now that you've already watched the video, because I did move that homework to Thursday. So homework number 14 is due on Thursday. Actually, I could take some questions on it in class today, potentially. So maybe during the break, I'll put a little spot for people to throw some problems up there. But I'll also take questions on Thursday over this assignment, which is based on the stuff that we started talking about on Thursday. And then there is another assignment, and I know I'm going backwards here. This is because I'm doing things a little out of order. I jumped into chapter 6 without having done chapter 5. So we'll be working backwards to homework number 12, and that one will be due on Friday. And so I'll be able to take questions on both of those assignments on Thursday as well. Okay, so and the homework for Friday is based more on the video that you watched, okay, which we're gonna obviously be reviewing this week as well. So anyway, so those are the two assignments for this week. They're just a little out of order in terms of the numbering. It's a little confusing. So I do apologize for that, but yeah, hopefully I'll be pretty coherent today. I'm a little tired, I will admit. The climb went great. I was doing so good. I felt very strong, and the day we hiked in, which was the day, so I flew up there on, what day was it, Friday? I flew up there on Friday, and oh my gosh, this mountain was just a snowy white mass of an amazing scenic thing, just rising above the forest and everything. And we hiked in to a campsite Friday night and slept on the snow, and camped out there at about tree line, just about 4,000 feet or whatever. And I knew the weather was going to be good on Friday. The problem was I couldn't get up there in time to climb it before the weather turned bad on Saturday. So on Saturday, we woke up, it was all cloudy and the wind had whipped up. And so we decided, well, we may as well go for it. We're here. So we got on our crampons and ice axes and helmets and all this stuff and started working our way up. And it was really going quite well. It's actually easier than a lot of things I've climbed in the past. It wasn't super technical. You almost could just think of it as a snowfield. It was just walking up the snowfield, and it just looks kind of cool to have an ice axe in your hand. You didn't really need it. So, yeah, but I just carrying that along, and we got up, or I got up, I should say, to a point where actually the cold and the wind. I have a really heavy parka. I have really heavy gear, very, very thick mitts. So I wasn't actually cold, but the problem was I got to a point where I couldn't see anything. I literally could not see from myself to Vinny, like this distance, about 10 feet, because the fog came in. And I've never been on this mountain before, and it's all white because of the snow. So they call that a whiteout. And I lost sight of people that were ahead of me. Now, I did have one of these Garmin trackers things that has a map on it, but you hate to rely too much on something like that. I mean, battery could die at any minute, or maybe you read the map wrong because you're trying to read it while you're squinting in the bright sun. It's just hard to do. I mean, simple things that you could sit on a couch that are easy to do, like just even zipping up a jacket, suddenly becomes very hard when it's like frigid cold and the wind is searing through you, and your hands are kind of numb, so you can't really function so well. So everything, even simple tasks, become kind of hard. But I would have gone up there anyway. I would have said, you know what, I'm just still gonna just go do it because I'm kind of a peak bagger. That's what they call me. It's like I'm checking off mountains. And I wanted to check it off. And I normally probably would have done that, except that I realized how beautiful it was from the day before when I hiked in. If it was clear, I said, I'm gonna have to come back here anyway. I want to see this thing when it's all beautiful, cleared off. So I decided, why torture myself? And possibly put myself in a risky situation. So we came down a little early on Friday, and that was fine. And then that was on Saturday. And then I spent the last 2 days just up there in the Pacific Northwest. I actually did a little hiking yesterday too, while I was up there. So that was nice, just local things, nothing too major yesterday. But yeah, so I've had a whirlwind, and just got up at 3 a.m. this morning to come back, and it'll take me a day or two to get back into my rhythm here. Hopefully, I'm going to make some decent sense tonight. I think I'll be okay. I think I'll be okay. Nothing wakes me up like talking about math, so I think I'm going to be okay. So getting back into where we're at, these two assignments are for this week, but I wanted to point out that next week on Thursday, we have a midterm. And so on our Canvas page here, which I've pulled up on the screen, if you go into the files section, like usual, there is a folder over here that says, if we scroll down, second midterm resources. So this thing is pretty much ready to go. I'll remind you, just like I did for the first exam, that everything in this folder is completely optional. I don't expect anybody to do all of it. This is too much here, probably for most of you. You have lots of other things to do. And it depends how you're feeling about the material. Maybe some of you want to try and give a go to a lot of these things just to get really as ready as possible. That's fine. Others of you might feel like, yeah, you're feeling pretty good about it anyway, and you don't have that much time, so maybe you're just going to pick and choose. I do have 2 sample midterms. Those are the things on the bottom here. One of them is in all lowercase letters. The other one is all capital letters. And those are from the last 2 or 3 semesters. I just took those exams, and the solutions are there, right? I'll just advise you again to try not to just read my solutions. It's easy to fool yourself into thinking you're totally on top of stuff when you just read my solutions or just listen to me. But in fact, where you really get a test of where you're at is when you're doing it yourself, right? So I would recommend you print out a blank copy of at least one of the 2 midterms. If you only had time to do one thing, that's probably what I would do. I just print out one of those sample midterms and just give it a try. See how it goes. If you have more time, I'd probably try them both because they're obviously not the same. So you get some variety of types of questions in there as well. There's also a review session, which is actually what this little hand is pointing to right now. There's a review session which has about 8 problems in it or something like that. And I have the solutions to those review session questions typed out right here. Or if you don't want to just read my solutions, you can watch my video about it. So if some people learn better by, I think by listening. And so if you go to pages, there is a link here. It says midterm 2 review session. So we can open that up, and I've got it broken down into a couple of files. The first one's the main part of it is like 90 minutes. And then another roughly half hour after that. So that'll take you a couple hours if you wanted to watch the whole thing, but you don't have to watch the whole thing, or you can watch it on double speed or something like that and make it go by a little bit quicker if you want to. Again, it's completely optional, completely optional. And then the only other thing, let me go back in here again, just the midterm 2 review. So I'll open up this document. This is the document that just sort of has all the nuts and bolts about the exam. The only thing I haven't put in here are extra office hours. I'm going to need a day or two to figure out when I'm going to be available next week. The test is on Thursday, so chances are I'm going to have some extra office hours on Wednesday, even though normally on Wednesdays I don't have office hours. Probably next week I will. And then what the exam is going to cover, all of chapter 4, which is going to be probably at least 50% of the test, maybe 60, could be at least half. That's a lot of sections. The 3 sections of chapter 5, which we're going to be mostly working on this week. And then section 6.1, which we started last Thursday, and which I'm going to try to finish up today, which is what homework 14 is about. So that's what the exam is going to cover. You can see all the buzzwords, right? All of the terminology. This is a good way to, in fact, I might even, if you have time, I would probably do this even before you try the sample midterm. Just go through this list of words and just, make sure you know what it's talking about. If something catches you by surprise, you're like, oh gosh, I don't know what linear dependent means, or oh, I don't think I remember what nullity is, or something like that. Then you can go back and refresh your memory about some of those things. But you can see how long the chapter 4 list is compared to 5 and 6. It's longer than both 5 and 6 put together, actually. So that gives you an idea. And then there's a bullet point list of all the things you should be able to do. And that would be another good thing to kind of view it as a checklist. It's a pretty long little list of bullet points here, guys, of all the things you should be able to do for this upcoming test. And so I think if you went through that bullet point list and then you tried either 1 or 2 of the sample midterms, my guess is when you come in here next Thursday, you're not going to be like surprised by very much that you're going to see. Like you're going to come in hopefully confident and hopefully seeing questions that are reflective of the stuff that you've reviewed. So it's just my advice. I haven't written the test yet, so I don't know, but that would be my idea. I do have a few extra problems here as well. These are also good questions. There's another, whatever it is, 9 of them here. These are also good questions that you can do that I have the answers to as well. So the solutions to that are the very first document, your midterm 2 review solutions. But again, I know not everybody has the luxury of infinite amounts of time to try all these problems out. So just do what you can. Give it a good go. This upcoming weekend will be a good opportunity to do that. There will be one more assignment for next Tuesday, which is homework 13, but it's not that bad, and I'll be able to answer questions on it in class and make it pretty easy. So I'm hoping that after these 2 homeworks come in, you're going to have most of the 6 days between Friday and next Thursday to be focusing on getting ready for the test. That ideally, that's how I would see the time working out, at least for this class. So, and I also forgot to mention, there will be an extra credit quiz coming as well. So you've done the video piece of it. I'll have probably another 3 problem quiz for you. That will probably be something I'm having you do over the weekend, this coming weekend. So I'll tell you more about that maybe on Thursday. Anybody have any questions about any of that? All right, so that's where we're at. Let me go ahead and mute that screen so it doesn't get in the way here. I want to start today by finishing chapter 6.1. So that's not what you just watched the video about, but it's what we were doing on Thursday last week. I didn't really quite finish it, which is why I wanted to push the homework to Thursday for this particular topic. We're talking about linear transformations. Now, these are just functions. I usually use a t to denote them. It's a function from one vector space to another. Usually we call the inputs would come from the vector space V. The outputs would come from the vector space W. Edgar? Yeah.
So like we use the word mapping.
Mapping.
Also,
Mapping is the same as function. Something that is a mapping is just a function. Yeah, it's just a function from V to W, and it is linear. It is a linear transformation, in other words, if T respects addition and scalar multiplication. Right, so that's the main requirement, and I put down the formulas here for T to respect addition, then T of V1 plus V2 should equal T of V1 plus T of V2. And scalar multiplication, T of K times V1 should equal K times T of V1. So you have to be able to factor the K out on that. And so that's really what it means for a function to be a linear transformation. We talked about this zero vector check. So if somebody gives you a mapping or a function and asks you, is it linear? The first thing you can do that's quick, it's a quick thing to do, is to just check, does T respect the zero vector? Does T of 0 equal 0? That's the first rule of thumb. If that fails, if T of 0 does not equal 0, then it's not going to be linear, and you could stop very quickly on that one. By the way, I'm using these little sub notations of V and W to emphasize that the zero vectors in the two vector spaces might not be the same. They like the universes could be different, and so the vectors might look different. So I like to keep them straight by putting the little V and the little W on those zero vectors there. Okay, so that's the definition. Last Thursday, we did about 4 examples of this already. And I want to do a couple more today to kind of get started here, warm up a little bit. And I've got one on the board all ready to go here. So let's read it together and see if we can work through this example. So we're going to define T. And in this warm-up example, the inputs are going to be 2 by 2 matrices. So M2 of R, that's 2 by 2 matrices. The outputs are going to be polynomials P1 of R. Those are polynomials of degree 1 or less. And you can see then that I'm going to give you the formula here. I plug in a 2 by 2 matrix, just A, B, C, D gets plugged in. Notice that the output over here is in fact a polynomial of degree 1. There's no x squared here. There's no x cubed. The only power of x that you have is just the first power, which it should be if this really is your W vector space, the outputs, right, coming from that space. All right, and then the question is going to ask us here, guys, is that linear? So is T linear? And I'm going to have to write it over here a little bit, solve it out for us. Does everybody understand this question? By the way, this 6.1, it'll probably be roughly 20%, 15 to 20% of our exam next Thursday. And a question just like this would certainly be in the running of the sort of thing I might ask you about. So let's see if we can do this one. This is a yes/no question. Is this transformation linear? What do you suppose I'm going to do first? Zero vector check. Exactly. So for my solution, I'm going to check the zero vector. And that means I'm going to take T of the zero vector. So in this case, that would be a matrix of all zeros. That is the zero vector. So that just means that the A, the B, the C, and the D are all 0. Now, if you plug those in on the right side, 0 for all of the A, the B, the C, and the D, you get 0x plus 0. Right? So there's, various A, B, C. By the way, you notice the D does not even show up in the formula. Nothing says it has to, right? This is just any old formula for a transformation. I'm making this up and giving it to you. Nothing says you have to see all 4 letters there. So, but what you do notice is that if you put in 0 for all of the variables, that's what you get. So does it pass? It sure does, right? This is the zero vector right here. So that's just a check mark on that. And so now let's see if we can check if t respects addition. So if it passes the zero vector, then we have to go on and check whether or not t respects the addition and the scalar multiplication. So for the addition, I have to take two matrices and add them together. So inside the transformation. So I'm going to do T of, and then I'm going to make one matrix A, B, C, D. And then I'm going to make another matrix. I'll just use S, T, U, V. You can use whatever letters you want. I would recommend not using X as one of your letters here because we are going to have X in the polynomials that come out of it. So putting X in here would potentially be confusing. So use any other letters you want. I'm going to just use S, T, U, and V. And then I want to calculate this thing. Okay. So what do I do first here, guys? What would be my first step? I'm not ready to actually use the transformation yet. The transformation knows how to take one matrix and give an output. But right now I don't have one matrix, I have two matrices. So what do I need to do first? Add them together, combine them together, right? My first step, before I even evaluate the transformation, I just want to add these matrices together. A plus S, and then B plus T, and then C plus U, and then D plus V. So I go ahead and do that. Okay, now I have a single matrix here. I have a single matrix and I can now go ahead and transform it by using the formula. Now, how does this formula work? Well, the X coefficient is 3A plus C. But in this notation, it would be 3 times whatever's in the upper left corner plus whatever's in the lower left corner, right? So this is going to be 3 times A plus S plus C plus U. All of that is times X. And then the constant term is 4 times the upper right corner, which was B plus T, and then plus the lower left corner, which is C plus U. So it's a little bit long-winded, but that's what it would look like, okay? Sometimes these things can get a little bit confusing halfway through. People are like, I'm not sure what I'm supposed to do with that. If you lose track of what you're supposed to do with that, remember, you can always go to the end of the process. At the very end, and you may not want to write this down yet because I may not be giving myself enough room, but this is just thinking about it. This is what we ultimately want to end up with. We want to end up with the separated matrices that are being transformed separately. The main thing you notice here at the end, guys, is that all of the A, B, C, D stuff is gathered together in the front, and all of the S, T, U, V stuff is gathered together at the end. So there's a lot of algebra I could do right now, but the main thing I want to be trying to do is get all of the A, B, C, D stuff together and get all of the S, T, U, V stuff together. So let's see if we can take everything that has like A's, B's, C's, and D's and put it in the front. Okay, so here I have a 3A and a C, right? So there's a 3A plus C. All of that is multiplied by X here, you see. And then where else do I have A, B, C, D stuff? I have a 4B and a C, right? So let's write that down, 4B plus C. So all of that, I'm going to go ahead and put some big parentheses around all of that. If you need to, just for bookkeeping, you can kind of underline, all right, I did the 3A, I did the C, I did the 4B, and I did the C, right? And then the rest of the terms would come next, right? So the stuff that has the S, the T, the U, and the V, I have a 3S plus U that gets multiplied by X. And then I have a 4T and then a plus U. So that would be the last part. And guys, if you look at this, I actually did a pretty good job of leaving myself the right amount of space. This thing right here is exactly T of A, B, C, D. This first blue part is exactly T of A, B, C, D. This second blue part would be T of S, T, U, V. See that? This is what we wanted. This is T of V1 plus V2, right? So in terms of the generic setup, we took two vectors, V1 and V2, we transformed their sum. And at the end of the day, we have T of V1 down here plus T of V2 separated. Yeah, so it is going to respect condition. And I want to mention, I mentioned this last week, but I'm just going to reiterate again that I don't want to see people manipulating on both sides of the equal sign at the same time, because that's too much simultaneous manipulation. It's hard to keep that clear. So try to only work on the right-hand sides of the equal signs and be sure to include these equal signs, but don't write anything under the left side. Okay, so this is a one-sided thing only. So far, so good? All right, let's check the scalar multiplication. So far it's looking pretty good. So far it's looking pretty good. It passed the zero vector check. Then it respects addition. So now let's check T respects scalar multiplication. Let's take a look at this. Okay, so you guys probably remember for the scalar multiplication, we bring in a K. So I'm going to take the scalar K times the matrix A, B, C, D and transform that. Okay, currently the K is on the inside here. Ultimately, we're going to try to get it to the outside, but I can't just pull it out right away. I have to show how that happens. So the first thing to actually do is kind of counterintuitive, which is that you actually want to feed the K all the way through the inside. So you actually do the scalar multiplication, and that gives you the matrix Ka, Kb, Kc, Kd. And I'm going to now take that matrix and transform it. Okay, so again, everywhere I see the A, B, C, D over here, now I'm going to be writing Ka, Kb, Kc, Kd. So the 3A plus C, that's going to be, what is that going to be? That's going to be 3Ka plus Kc, all of that times X. And then the constant term, which was originally 4B plus C, now becomes 4Kb plus Kc. Like so. And what are you going to suggest I do with that? Every single term has a K in it, right? I can totally factor that out. It's just algebra. So just go ahead and pull the K all the way out. And after you do that, you'll have 3A plus C times X plus 4B plus C. So you have that K all the way on the outside, and the part in the brackets now, my friends, is just T of A, B, C, D again. So this just becomes K times T of the matrix A, B, C, D. And again, one more time, I'll just remind you, we're going to have white space here. Only writing on the right-hand side. But this is also a check mark on this one. This is also working. And so my answer then, my ultimate answer is yes. T is linear. This is a linear transformation this time. All right. What do you guys think? Any questions on that? So we've seen a few of those. I would like to show you one more. But this next one is really important. It's actually not just one example. It's going to be an entire theory of linear transformation. So let me give myself some room. Are you sure there's no questions though? Are so good? Okay. I want to talk about, and this is what I had run out of time for on whatever day it was. Yeah, I want to talk about another example, and this one is really, really important. Okay. This isn't just a one-off example that's never going to show up again. This is actually kind of an entire theory. What I'm going to do for a moment, guys, is I'm going to fix any matrix. Let's say it's an M by N matrix capital A. Okay, so it's M by N. Let's fix that matrix. And what I'm going to do then is I'm going to use that matrix to make a linear transformation. And here's how I'm going to do it. I'm going to define T. And T is going to go from Rn to Rm. So my inputs are going to have N slots. My outputs are going to have M slots. And I do want to note the order here. The matrix was M by N. And now here I'm going from Rn back to Rm. The switching of the order of the M and the N is absolutely critical. So you have to switch the rows and columns when you're setting up the V and the W in this notation that we're talking about right here. Okay, so I'm going to make a transformation. And how am I going to do it, guys? Here's what I'm going to do. I'm going to take T of X. And I am going to make a output by just simply taking A times X. Let's put this in a box. This is a big deal right here. Okay. I first want to just make sure this even makes sense. A is M by N size. And I'm multiplying that by this X. Now, X is an input. So since it's an input, it lives in Rn. That means there's N slots, and I can view it as a column with N entries in it. So in that case, it's like an N by 1 matrix. It's a single column. If you multiply an M by N matrix by an N by 1 matrix, what size do you end up with? Sorry, Nathaniel? No, if it's one more time. M by 1, right? So remember, these two numbers have to match, and then the size becomes this one by this one, right? M by 1 is exactly what the vectors in Rm would look like, right? They could be thought of as a single column with M slots in them. So absolutely, this makes sense. You're plugging in N slots, and you're spitting out M slots. Now, I claim that anytime you make a transformation by doing that, it is linear. So I claim that T is linear. And I'm going to show you that it respects addition and scalar multiplication. Okay? So let's just check it here, guys. T respects addition. I'm going to skip the zero vector check. I'm just going to go straight to the two properties for now. So let's check that T respects addition. So that means I have to plug in two vectors that are going to get added together. Let's say they are X and Y. So let's say I want to look at T of the quantity X plus Y. So I'm kind of just following this rule of addition here. Now, the way the transformation works is that we just take our input and we pre-multiply it by A. So we're just going to put A in front of X plus Y. And what do you suppose I'm going to do with this? You're stranded on a desert island. You can't get off unless you tell me what the next step is.
You're gonna plug in the
Plug in what?
DA. So you can make it AX, AY.
Okay, I would call that distributing the matrix. Yeah, we're going to distribute the matrix. Exactly. That's the only thing I can see to do here, guys. Distribute the A, right? AX plus AY. That's exactly it. But guys, AX, that is just T of X. And AY is just T of Y. And so it respects addition. So it respects addition, and that's very short and easy to write down. Okay? And so it respects addition. I know it looks very abstract, but that's actually the power of it. If I gave you a specific matrix with a whole bunch of numbers, this would suddenly be a mess, this whole whiteboard. What I've done here is I've defined something so abstractly that the write-up has become incredibly short and simplified. All right, and the scalar multiplication is going to be the same thing. Let's just check that as well. T respects scalar multiplication. So again, how's this going to work? We're going to have T of K times X. This time we have a scalar, which is K, and it gets scalar multiplied by X. Well, how does T work again? T works by just multiplying by A. So I'm going to multiply by A in the front, and then I have a KX. So A times whatever you plugged in, which in this case is KX. Now K is just a number. Of course, we have to be careful because with matrices, we've learned you can't switch the order of matrices when they're being multiplied together. But here, I don't have two matrices. What I have is a matrix and then a number. And I can put the number in front. So I can put the K out in front and then put the A next in front of the X. And now I get exactly what I want, which is K times T of X. So that's another check, right? This is also checking that this thing actually works. Okay, so T respects addition, T respects scalar multiplication. So are we okay with that? Any linear transformation of this type is actually called a matrix transformation, and I think that's probably worth writing down. So I'll just make this as maybe a remark really quickly. Any linear transformation of this type is a matrix transformation. And matrix transformations are always going to be linear. They're always going to be linear. That's kind of a nice fact. Okay. So by the way, again, don't forget, I'm still doing my white space. Trying to be real good about that on all of these verifications. More white space on the left side. So the formatting of these, I think by now I've kind of hammered this home quite a few times. I hope it's making some sense how I want these things formatted. Okay, so let me understand this. If I'm given any matrix whatsoever under the sun, any size, any matrix, I can make a linear transformation using that matrix. That's what this is about. So let me just give you a quick specific example now. Let's just make a really specific example. So example, let's suppose that A is the matrix 1, 2, and then 3, 4, and then 5, 6. Right? What I want to do here is write the associated linear transformation. So there's a natural linear transformation that is associated with it. Okay, so let's see if we can solve this as a little example here to kind of understand what's going on. What we're going to do to write this linear transformation down, and that just means that we are supposed to define T. And by the way, for this matrix, T would go from R what to R what? It all comes down to the size of the matrix. You can see that here. If A was M by N, then that defines a transformation from Rn to Rm. So probably before I even take a breath, I want to write down what's the size of this matrix, which is 3 by 2. We got to make sure we get the M and the N in the right place here. That is a 3-row, 2-column matrix, 3 by 2. And so the transformation then goes from R what to R what? R2 to R3, right? Remember, the M and the N are gonna switch positions. So this is gonna give us a transformation from R2 to R3 via T of, now I have to plug in something from R2, which is gonna have two slots. I'll call those slots X and Y. And the question is, what is the actual output now? So the way that the transformation works is we take the matrix times the vector. So in this case, the matrix, let's just write it here, 1, 2, 3, 4, 5, 6. That gets multiplied by the vector, but guys, I'm going to represent the vector as a column, not as a row. So you see n by 1. In this case, that would be a 2 by 1 column, which is just going to be X and Y, like that. Okay, so here I'm taking a 3 by 2, and I'm going to multiply it by a 2 by 1, and my answer should end up being 3 by 1. Let's just check out how it goes. So we all know by now how to multiply these matrices, I think. So we go across the rows of the first matrix and we dot those row vectors with the column X, Y. And when I do that, the first entry is going to be X plus 2Y. So we put X plus 2Y right there. Okay, and then for the second row, we have 3X plus 4Y. Like that. And then for the third row, we have 5X plus 6Y. Like that. And so that would be your output. So it says write the associated linear transformation. This is it. That's the answer. Now, truth be told, you didn't really need to, I wouldn't recommend crossing this off of your notes, but just so you guys are clear, you know, you could have pretty much figured it out directly. You say, well, the matrix numbers have 1, 2, 3, 4, 5, and 6 in them, and notice that that's exactly the numbers that you're putting in right here as well. So it's not exactly a surprise how that works out. So some of these homework problems for this assignment on Thursday, they're going to give you a matrix and ask you to write down the associated matrix transformation. And it's just what we just did right here. It's just what we just did right here. Does that make a little bit of sense? Now, you could also imagine, if I ask you to prove that this is linear. Haha, let's just do this. Let's just do this. Let's just do this. Let's suppose that I start over and I say, I'm going to define T from R2 to R3 via T of XY equals, and then let's say I give you X plus 2Y, 3X plus 4Y, and 5X plus 6Y. Let's say we write it just like that. We define that transformation, and then I ask you, is T linear? Let's just pretend for a minute that we don't see the left side of the board at all, and all we see is that question. Okay, so let's just imagine we have amnesia all of a sudden. We don't know that we just did this thing here, and somebody just hands us this problem, which is almost the same thing as how the warm-up was, right? I just gave you a transformation and I just said, is it linear, right? So of course, the way we did this warm-up problem, right? We did the zero vector check. Then we stopped and we verified that T respects addition and scalar multiplication. We could do that here too. You would have to, you know, have another vector on hand. You'd have X and Y, and then you'd have to make another one like for the closure under addition, or for the respecting of addition, you'd have to have like an A comma B. You have to like add them together, have to do a whole bunch of algebra, right? You've seen a few of these where it's been kind of messy, right? This one wouldn't be so bad, but I promise you I could make one that would be much worse, right? I could just make more inputs and more outputs. I could give you a ton of inputs and a ton of outputs and say, show that it's linear. And if I do that, you're probably gonna be freaking out that, oh, this is gonna take a whole page just to write it out. It's kind of messy, right? But we have a fast answer to this problem now. If we recognize, first thing we need to notice is it's going from R something to R something. Okay, if my transformation is not going from R something to R something, then we're not talking about this matrix transformation stuff. Then we've got to go back to T respects addition and scalar multiplication. But if I give you a transformation from R something to R something, then there is a really good chance that I have in mind a matrix transformation. And what you can do here, guys, is you can just say yes. You can say yes, since T is a matrix transformation. And the only thing I would ask you to do is to tell me what the matrix is. So you should tell me what the matrix is. But guys, the matrix is staring at you in this formula. You see all these coefficients, the 1, 2, 3, 4, 5, and 6. Those are telling you what the rows and columns of your matrix A are. That justification in blue right there would be 100% full credit. You don't have to write anything else. You don't have to check the zero vector. You don't have to check that it respects addition and scalar multiplication. If you recognize that the function that's been given to you, the mapping that's been given to you, is actually a matrix transformation, you can quote that. You can just say, this is a matrix transformation, therefore it's linear. It's kind of like, remember back when I said anytime you take the span of anything, it's always a subspace? And you could just say that. You don't have to check if it's closed under everything. Same thing here. If you recognize that this is a matrix transformation that you're looking at, you can just say that. You don't have to then go on and verify that it respects addition and scalar multiplication. See what I mean? So it's a shortcut. It's a shortcut. It's a shortcut, but it only works if T goes from Rn to Rm. Don't try to use it if I see polynomials or if I see matrices, like something like this, there's no shortcut. Something like this, you still got to go through. Does it respect addition? Does it respect scalar multiplication? Right. Okay. Now, you can also, yeah, so in this example, it's kind of interesting. In this example, I gave you the formula for T and asked you to basically write down what the matrix is. You basically extract the matrix from the formula. Whereas here, I started you off with the matrix and asked you to write down the formula. So you can play this game in both directions, right? Given the matrix, given a fixed matrix, there is a matrix transformation, right? That's linear. Conversely, given the formula for the transformation from Rn to Rm, you should be able, if it's a matrix transformation, you should be able to write down the matrix for me. So you can go back and forth and back and forth, right? I want to point out something else about that matrix, though, that's going to come up on the homework, because it was pretty easy to see what that matrix was, but there might be some cases where it's maybe not quite so obvious. So I want to continue discussing this same follow-up example of figuring out what that matrix is. I mean, you kind of get the idea that I just wrote down this matrix by just looking at these numbers that are up here. That's a little loose. That's a little bit loose. I want to be a little bit more precise. So continuing this example, I'd like to note, what I want to note for you here, guys, is that there's two very important inputs to that transformation. There's two very, very important things that I can plug into here. And that is 1, 0 and 0, 1. Those are the standard basis for R2. And let's see what happens when you plug them in. T of 1, 0. If you plug in 1 for X and 0 for Y, into this box equation, 1 for x and 0 for y, what am I gonna get? 1, 3, 5, right? 1, 3, 5. If I plug in 1 comma 0 into t, the output is 1 comma 3 comma 5. And do we see 1 comma 3 comma 5 anywhere in the matrix? You wrote down in blue over here. It's the first column. It is the first column. That is exactly right. So this is equal to the first column of A. Right? And then the other important value is, and t is 0, 1. If you plug in a 0 for x and a 1 for y everywhere, what you'll notice, hopefully, if you plug it in correctly, is that you get the values 2, 4, and 6. And as you can see from the matrix, those exactly give you the second column of A. In general, and this is going to be a box-worthy observation here. We're going to put this in a nice box. The matrix associated with T, which is going from Rn to Rm, is the M by N matrix, which we've been calling capital A. What I'm trying to do now, guys, before I go any further, I'm flipping the start of this conversation on its head. When I started this conversation, I said, let's start with a matrix and then create the matrix transformation. What I'm doing here is I'm saying, let's start with the transformation. And now the question is, what's the matrix? Right? And it's actually very easy to get this matrix now. So A is the following matrix. The first column is going to be T of 1, 0, 0, 0, 0, 0, 0, 0. That's a column. And then the second column is going to be T of 0, 1, 0, 0, 0, 0, 0, 0. And so on and so on and so on. The last column, dot, dot, dot. The last one is going to be T of 0, 0, 0, dot, 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 1. So you're just evaluating the standard basis vectors for Rn. Notice there's going to be n columns here. N columns. You're just evaluating each of those standard basis vectors. It's exactly what I did in the note up here. I figured out what is T of 1, 0, what is T of 0, 1. I got my 2 columns of my matrix from that alone. Because guys, sometimes they're going to ask you, what is the matrix of the transformation? Here is a beautiful way to write it down. It's a beautiful way to write it down. Now, having said that, should I do one of your homework problems for you? Yeah, I think I'm going to actually. This is going to be, I just got to find it again. Having said that, I'm going to do a problem from your assignment for Thursday. And I hate to steal your fun. Are you sure? It's okay? All right. I mean, I actually like doing it, but I also should, it's okay. I'm going to do it. You'll find some of these in the review materials too. So you'll get a chance to practice it yourself. So let's do one more example, and then I think I'm going to be good with this topic. This is actually, for those of you following along with the homework, this is 6.1, number 28. So this is from the homework that's due on Thursday. And what it does is it says, find the matrix of T. So when they say matrix of T, they just mean they want you to find this matrix that we're talking about right now for the transformation T. And T is going to go from R4 to R2. But I'm going to throw a curveball at you here. Instead of giving you the full formula for T, like I did in the follow-up question over there, where I gave you in the box, I gave you the formula. Instead of doing that, I'm going to give you some random values here. I'm gonna tell you that T of 1, 0, 0, 0 is 3 comma -2. And then I'm gonna tell you that T of 1, 1, 0, 0, that is going to be 5 comma 1. And then I'm going to tell you that T of 1, 1, 1, 0 is going to be -1 and 0. And finally, T of 1, 1, 1, 1 is going to be 2 comma 2. So I did not give you a formula for T. If I had given you a formula for T, you could have done what we did in the note. You could have said, okay, let's figure out the first column of A by doing T of 1, 0, 0, 0. And the second column, 0, 1, 0, 0, and so on. I could have done it that way. But here I've given you T of sort of a rather random looking set of 4 vectors. So how in the world are we going to do this? Let's see if we can figure it out. Maybe some of you already have an idea. First thing I always like to do is figure out what's the size of my matrix going to be. The size of the matrix for this example would be what size? 2 by 4. Guys, this is a transformation from R4 to R2. Remember, you got to switch the order of the M and the N. So this is going to be a 2 by 4 matrix. Let's kind of prepare ourselves for that. It's going to have 2 rows, 4 columns. It's going to be kind of a wide matrix like what I'm showing here. And I've given you here this general comment about how to write down this matrix. The first column of A is just T of 1, 0, 0, 0. Well, actually, they did give us that. They did give us that. So we can just go ahead and put that into the first column. No problem. So far, so good. That part's easy. But the second column is supposed to be T of 0, 1, 0, 0. And they did not give us that value. They did not give us T of 0, 1, 0, 0. My question for you is, can we figure it out? Yes, Mr.
We made 3. So 3 plus a variable is equal to 5. And this is equal to
I know what you're trying to say, and you're on the right track for sure. I think we can maybe phrase it a little bit more like directly to the point here, Anthony.
T to the second. No, T is 1 of the first column, plus T to 1 of the second column.
It's kind of same thing he's saying. Yeah, that would work. I want to do something that's really easy. Like, can we just directly figure out how to express this vector that we want by using the data that we have been given? Okay, guys, remember that T respects addition and scalar multiplication. It also respects subtraction because, subtraction would just be a -1 scalar. And so we can actually get this vector as the second vector minus the first vector. Do you see that? This is just T of 1, 1, 0, 0 minus T of 1, 0, 0, 0. That's the observation. And it's more or less the same thing that you guys are saying, but just kind of in the getting straight to the point here. So in other words, writing this vector that we don't know in terms of 2 vectors that we were already told how to transform. So T of 1, 1, 0, 0, that would be 5 comma 1. And from that, we have to subtract T of 1, 0, 0, 0, which is 3 comma -2. And if we just do that subtraction, we will get 2 comma 3. And that becomes the second column of our matrix. See that? So that's pretty slick. So we get the second column of our matrix. Let's try and get the third column. Can anybody see how I can get the third column of A? The third column of A should be T of 0, 0, 1, 0, which we were not given, but can we make it out of what we were given?
third vector is the second column, second vector.
if I take the third vector, which is 1, 1, 1, 0, and I subtract 1, 1, 0, 0, I would get 0, 0, 1, 0. That's exactly right. So this is T of 1, 1, 1, 0 minus T of 1, 1, 0, 0. Third vector minus the second vector. Remember, guys, this is only true because T is linear. T respects subtraction. And so this would be, the third vector is -1, 0 minus 5, 1. There you go. And -1 minus 5 is -6. And 0 minus 1 is -1, and that goes into the third column. -6, -1. Awesome. And finally, can somebody tell me how to get T of 0, 0, 0, 1, which is going to be the last column of the matrix? One more time?
Say repeat,
Rinse and repeat, right. Which vectors am I gonna use?
1.
4 and 3, right? If I take the fourth vector minus the third vector here, subtract these two, you get 0, 0, 0, 1. Now, if I subtract the outputs that go with those vectors, I'm going to get 3 and 2, I believe. I'm going to get 3 and 2. Okay, and that's your matrix. This would be the answer. This is the answer to the homework problem. Now, in case you're wondering, we can then write down the actual formula for the, see, this is just T of 4 points. It's like, what if I want to know T of some other point? Right? Well, we can do that now because we have the matrix. Once you have the matrix, you can write down T of anything, right? In general, what is T of X, Y, Z, W? If I take any 4 inputs there, well, that's something in R4. I have to spit out something in R2. How does it work again? We take the matrix times the vector. So I'm literally going to imagine putting X, Y, Z, W as a column vector here and just doing this matrix multiplication. The top entry is going to be 3x plus 2y minus 6z plus 3w. And the bottom entry is going to be -2x plus 3y. Again, you don't need to do this for the homework, but I would write this down if you want to have this to help you understand it later. That second row of the matrix A gives you the second entry of that output transformation. So this would tell you T of anything. You can try plugging in any one of these 4 points into this vector here. I promise you, you'll get these 4 outputs. But now you can take T of 7, 7. Sorry, no, you can't. You can take T of 7, 7, 7, 7. I gotta have 4 inputs. Or you could take T of 5, 6, 7, 8. Or T of 29, 30, 35, 52, whatever. Pick your 4 favorite numbers. You can take T of anything using this formula. See that? Once you have the matrix in your hands, you have full, complete information about what your transformation does. You guys don't look nearly excited enough about this, right? What I'm trying to say is that if I give you just a minimal amount of information about what your transformation is doing, let's say you're a computer graphics designer and you want to move some image around on a screen, right? And you'd say, this pixel is going to move there, and then this, whatever's in this pixel is going to move here, and this is going to go here. And I tell you where 4 pixels go, and based on that, you can tell me where every other thing in your screen gets moved to, just based on that minimal amount of information. That's really a strong application of the linearity of a matrix transformation. So things like rotations, those are always linear. Reflections across lines, those are always linear. Sort of stretching, its technical word is it's a shear. If you take a shear of a XY plane, you still have, that's a linear operation. So again, if you tell me you have 2 of the points on your on your domain are being affected by your transformation, then I'll be able to tell you how T affects every other point on that domain. Hugely powerful idea here that we're talking about. Yeah, so in other words, guys, I have been mostly telling you about, oh, here's a transformation, tell me, decide, is it linear or not? Yes or no? And we've had to check that T respects addition and scalar multiplication. Or now we have this new idea that maybe if it's from Rn to Rm, it might just be a matrix that we can use to represent that transformation. But nowhere until now have I really told you why you should care about this. Who cares if T is linear? It's just a function. Who cares, right? Well, now I'm giving you a reason to care, right? If you have a linear transformation, I can give you just a minimal amount of input information, and from it, you can construct so much more. So much more. Let me give you one more example, and then I promise we're going to take a break. I am so excited about this.
You see me wait.
I am so into it. I am so into this. So let's just do one more example. And you're gonna have some of these on Thursday's homework as well. So we'll get more time to practice it on Thursday. But one more example here, I think, and then we'll take a little break. Okay, so here is an example. Assume that T goes from P1 of R to M3 by 2 of R is linear. Assume that it is linear. Well, that's already different than anything I've done with you so far. I'm usually not starting off my examples this way. Usually I'm starting off with a formula for T and I'm asking you, is it linear? This is quite different. This is quite different. I'm saying, assume we know it's linear already. I want to leverage the power of that. I want to use that information to help me. Sorry, it is linear. I'm not done with the sentence yet. Assume that this is linear with T of 2 is equal to the vector -4, 2, then 3, 0, and then 1, -1. And then T of 1 plus X is going to be equal to the matrix 6, 2, -1, 1, and 0, 3. And then what I want to do, guys, is based only on that, I would like to compute T of any A plus BX. In other words, I'm really saying, I want us to completely define what T is. I want to know what T of any polynomial in P1 of R is, just based on the two inputs that I told you. I told you where 2 pixels get moved. I want to know, where does the rest of my screen get moved to? Isn't that amazing? That I'll be able to tell you, this is infinitely many inputs here, but I can tell you what they all are, how they all get transformed, simply because I told you these two. And by the way, I think I told this to you wrong. Sorry, I messed up this first matrix. Can I fix the first matrix? I got ahead of myself. Let's try the first matrix again. I wrote it down wrong. I'm so sorry. It should have been -4 and 2, and then 6 and 0, and then 2 and -2. Any mistakes I make tonight, I'm blaming on sleep deprivation. There we go. So that's my matrix. All right, let's see if we can solve this, guys. And the faster we solve it, the faster we'll take a break tonight. Let's just see if we can do it. So the idea here, guys, is that, you know, if I want to know what T of A plus BX is, remember, T respects addition and scalar multiplication. I can write this as A times T of 1 plus B times T of X. Like I can, remember you can bust out the scalars, you can bust out the plus sign. Actually, if you want to say it real simple, I can just say T respects linear combinations. After all, linear combinations are just made up of addition and scalar multiplication. If T respects those, then it's going to respect any linear combination, like the one that I have right here. Okay. So all we have left to do, guys, is figure out what is T of 1 and what is T of X. If I know what those two values are, I win. Now the problem is, I didn't tell you what T of 1 is, and I didn't tell you what T of X is. I told you what T of 2 is, and I told you what T of 1 plus X is. So I kind of gave you the wrong inputs here for what you really need over there. Do we have a way of getting the information that we want, even though the wrong stuff was given to us? Hang tight, Anthony. I'm gonna see if maybe somebody I haven't heard from yet wants to give this a try.
Wait, for T of 2, can I just divide it by 1 and that's how we obtain?
Divide it by what?
By 2.
Yeah, technically we don't do division in a vector
Always.
space, but we can do a scalar multiplication by basically what you can do here, guys, with this T of 2 is you can view it as 2 times T of 1, right? After all, this is just a scale. This is like a K value. K times T of a vector, well, I can put the K on the inside. Yeah, so actually that's exactly right. I'm just going to note here, guys, that T of 1 is simply 1/2 of T of 2. And so that would just be 1/2 of the vector that they already gave us, which was -4 and 2, 6 and 0, and then 2 and -2. And if I just cut everything down by 1/2, I'll have a -2, a 1, a 3, and a 0, and then a 1 and a -1. Just like that. That's T of 1. So I know what T of 1 is. But I also need to figure out, according to the setup that I have here, I also need to figure out what T of X is. Does anybody have an idea how I could figure out what T of X would be? The trick is going to be to figure out how can I make X out of what I already know. I already know what T of 1 plus X is. I already know what T of 1 is. Can I make X out of that, Angel? Exactly, guys. And we're kind of doing the same trick we did on this homework problem. We're kind of doing the same thing we did on the homework problem, except now it's with polynomials. But it's exactly the same idea. I can think of X as just being 1 plus X minus 1. And we know what both of those are. So we have our matrix for T of 1 plus X. It was 6, 2, -1, 1, and then 0 and 3. And then T of 1, we just worked that out a moment ago. It was -2 and 1, then 3 and 0. And the last row was 1 and -1. And we can just subtract these. We can just subtract these two matrices now, slot by slot. Yeah, so let's just do that. If I subtract these, I think I'm going to get an 8 and a 1 on the first row, a -4 and a 1 on the second row, and a -1 and a 4 on the third row. That should be T of X. All right. And so let's go back over here. And so what is T of, let's finish it right here. What is T of A plus BX? Well, it's equal to A times T of 1 plus B times T of X. And we already know what these things are. So this is just A times that first matrix that we just wrote down. And the first matrix that we just wrote down was -2 and 1.
3, 0,
And then 3, 0.
1,
And 1, -1, like that. Okay, that's the first one. And then to that, we have to do plus B times the second matrix that we just worked out, which is 8 and 1. And then -4 and 1. And then -1 and 4. That would be okay as an answer, the way I have it now. For reasons that are going to be more obvious after our midterm, but later on in chapter 6, it will sometimes be to our advantage to actually clean this up and write it as a single matrix. So I can do that very easily, and I think I will since it's already right here in front of us. Like I can just add the corresponding entries. So the upper left corner is really negative 2a plus 8b. And the upper right corner is just a plus b. And then if we go to the left middle slot, we would have a 3a minus 4b. The right slot is just b. And then the lower left corner is a minus b. And the lower right corner is negative a plus 4b. Does everybody see how I'm doing that? Everybody understand? I'm just scaling the a into these entries and scaling the b into these entries, then just adding it together. This gives me one single matrix. So now you can evaluate T of anything you want. If you want to know what T of 25 plus 72x is, you can do it. Just put in 25 for A and 72 for B. You can evaluate T of anything. This is the power of linearity. I only gave you 2 pieces of information. And from it, we were able to construct the entire function. T of anything can now be calculated because we just knew only those 2 pieces of information to begin with. It's very, very powerful. Questions about any of this? Okay, if not, guys, let's take a 10-minute break, and I gotta calm myself down. I'm too excited. During the break, if anybody has any questions on the homework from this section, you can write them over here, and I'll see if I can find some time to do it. Otherwise, we'll start chapter 5. Start going over what we did in that video when we come back from our break. See you soon.
The one that's not too, but that's what it's. Yeah. Now it's more. Yeah, yeah. Just.
This next goes. I had it this week, consecutively.
I wouldn't. It's just the voice. Yeah. Yeah. I went back.
So the gym setting there. So, I think he's gonna continue.
Yeah. It was just like. Yeah, I don't know. I didn't really want
Sit there.
Yeah.
And then we'll see.
Yeah.
But at least you get that.
People sound.
Honestly, it's like, I was gonna put it, but it's like that. She's like. But she seems like she's there.
But then I just, yeah, but then I thought that, you know, that's kind of. Yeah.
Andre's like,
You know?
yeah.
That would be good to.
That will probably be me for the next few days.
Yeah.
Right. Right. That reporting Thursday. Sun is tomorrow. And he was passive and then pressed on birthday. And what's all of it is to yeah.
They didn't say.
No spring a lot of it, so I have to.
Then you're using more, you know.
The ones who said, I do it.
I mean, I finish homework on this in the day, that's the day, it's just a little fun. It was like, who passed by her? Like, I don't care at all. I just don't want to.
Yeah.
All at the same time. This is, this deadline.
Never done the game.
Finally, they see you rolling around with a monster.
Okay.
Should be done. What ADHD? Thinking about me, my birth property, since you guys need to use English to follow.
It's kind of pretty.
There's a family, it's like slow learning or something, but he takes it to them. With like a month or two. He's like, yeah, I don't feel anything.
It's used to.
He just used to it. Let's see what I'm granting. It's like doing all this work, graduating, 5 years later, it's just that wrong. Jeez. My daughter is my. It was like a school graduation party. That's me with my young. Like that. No, I'm feeling like. Yeah.
I'm doing good. I'm a little tired, but I'm getting better now that I started class. Wakes me up sometimes. Supposed to rain here? It already rained? It was kind of a rough ride into the airport this morning. We did any winter reports on? I did want to say. Yeah, it just happened to snow like on a Thursday, back in the middle of February, and then I went to the train out for my adventure, so I went out and I didn't realize how much snow there's gonna be. I was gonna find two now, but so I just did the one and I came back. Like, that's enough for me. But yeah, I've had that trip, I just kept it shut on my mind. And now I'm kind of honestly, I don't even know why it's like there, but like. Yeah, their parents. That's usually my favorite hobby. I'll come up after me. That's you? No, this actually isn't me, but I'm gonna tell you about it.
Oh, this is like a little bit sunny, huh?
Yeah, I guess it is kind of time to start. Guys, I thought I'd just show you a little slideshow. I promised you some pictures, right, for my adventure. So I went with this guy that I went to grad school with at UC Berkeley, and he has a dog, a blue heeler. I'm not really much of a dog person, but this is the most nicest dog in the world. You don't have to do anything. It just, like, it doesn't bark and it just goes with you. Like, if you start walking up the trail, it just follows you up the trail. So anyway, that's my buddy. And my buddy is more of a skier, so he's hauling the skis on his back. Until now, and then finally there was enough snow that he put the skis on. He's like skiing up this trail. It was really pretty easy. This is what we did on the first day going in there. You can kind of see, just look at the dog. The dog is just like so obedient. And that dog has climbed really hard mountains, like all the way to the top of these big volcanoes. I'm really impressed with that dog. But anyway, so that was that. And then we finally started getting views of the mountain, so you can kind of see through the trees there. The mountains, yeah, it is really, really pretty. If I can make this a little easier to see. And then now it's really got snowy in a hurry. And you can see all the ski tracks in through here. And so the first day we had great weather. I was like, oh, we should have been climbing the mountain that day. I would have made it for sure. That's me with the dog. And then that's a huge mountain behind me. This was Mount St. Helens, by the way, which is the mountain that exploded in 1980. It erupted. It's a very infamous mountain. I think 57 people died and there was $1 million of damage from this thing. So that mountain is actually not as tall as it is, as it used to be. It used to be even taller before the eruption. So let's do more pictures, kind of working our way up, and then yeah, it's so white everywhere, totally white. And that's Mount Adams. I climbed that 3 summers ago. It's kind of off in the distance there. But the views were great, and we got set up here on the snow for our nighttime camping. And that was pretty fun. I was so jealous of my buddy because it was cold and he had the dog.
Oh.
In the tent, keeping him nice and warm. I was like, where's my heating pad? I had to suffer in the cold. Anyway, the sun goes down and that's kind of what the mountain looked like. I mean, this thing is totally white, totally white. You have to love snow to do stuff like this. The next morning, now this picture is now the next day, and you can see the sky, right? Oh boy. I woke up, I was like, I don't know, let's see how it goes. And so now it gets steeper. We're going straight up the steepest part of the mountain here. And eventually, that's me. At this point, you have to have a helmet on. And the snow is so bright, even on a cloudy day, you have to wear sunglasses and sunscreen and everything because it is just so bright. And still nice views, at least for a while. That's Mount Hood, which is the highest mountain in Oregon, which I climbed in 2018. That Mount Hood is much harder than the one I'm doing right now. But anyway, you can see it's getting kind of lonely up there and not that many people going up. By this point, I had to have my big Eskimo parka on because it was really windy and cold. And it's still going up, but see how the clouds are coming in? Yeah, it started to get very foggy. And that was actually ultimately the problem. I can still see the people climbing in front of me for now, but even a few minutes later, it starts to look like this.
Wow.
Yeah, I mean, it was 30, 40, 50 mile an hour wind gusts, and I could barely see anybody. At that point, I was like, I don't know if this is a good idea. And I also wasn't sure that it was going to be a very good view at the top. So you can kind of tell, you can't tell the difference between where the mountain is and where the sky is barely. I mean, it's really hard to see. So at that point, we came back down and of course it clears off later. I mean, we get a nice view again, but yeah, so anyway, I just love this stuff. It's just a really fun hobby. It's keeps me in shape. And so if you guys wonder what I'm doing on when it's not Tuesdays and Thursdays, I'm dreaming about doing stuff like this. So anyway, just wanted to show you a few of those pictures. That was kind of the Reader's Digest version of it. But it was a lot of fun. So I had to do that. I only showed that because my students in the past have told me they like to see what my hiking adventures are. Yeah, I better at least show a couple pictures from time to time.
Which year, like, how much does it weigh?
Oh, gosh, it could be pressing 50 pounds. Yeah, the tent is heavy. I have relatively good gear. It's, of course, the lighter it is, the more expensive it is. I try to get the better gear if I can, but crampons are very heavy. My buddy used skis, and when he was walking with the skis, it's very heavy because the lower part of the trail didn't have any snow, so he had to walk. So his pack was worse than mine at that point. But then he got to ski down. I sat down on my butt and sledded down, but it's not nearly as fun as skiing down. Yeah. So anyway, just thought I'd give you a sense of my other life that goes on when I'm not in here. Yeah, so what I want to do, guys, at the last part of our class today is kind of review the stuff from the extra credit video that you guys have watched. Chapter 5 is about inner product spaces. And this is just as I said in the video, it's just a vector space together with some geometry ideas. Sort of equipping the vector space with an inner product, which is kind of like a dot product. I even used that as an example in my video. And dot products, as you know from calculus, are very related to the geometry of the three-dimensional space that we live in, right? You see the dot products everywhere. But the way this works is that mathematicians have extracted the main properties of dot products, just your good old garden variety calculus dot products. They've extracted those definitions from the dot product, those properties of the dot product, and they've just thrown them into the axioms of an inner product. And you will want to know these axioms because on the midterm, I may ask you to verify. I might say, verify the axioms of an inner product. Or I might say, is this a valid inner product? In which case you'd have to know what the axioms are to answer that question. So make sure that you know these. I've listed them in the same order that I did in the video. You probably don't even need to, some of you are writing it down, it's fine. You don't probably need to, it's going to be in your notes already, but it's fine to rewrite it. This first axiom is the one that often fails when something fails. So I like to do it first because it has a good chance of being remember, just like everything else, if something fails from this list, if any one of these axioms is a no, then it's game over. It's not an inner product. And guys, if it's not an inner product, then I can't do any geometry with it. I can't talk about norms. I can't talk about angles between vectors. I cannot do any of that unless I actually have a valid inner product in my hands. Okay, so on the homework for, I guess it would be Friday's assignment, they're gonna give you some proposals of inner products. They're gonna ask you, is it a valid inner product or not? And you're gonna be focusing, you're gonna need to be focusing on this list right here, okay? And going through 1, 2, 3, 4. In the video, you saw me do that. That's the reason it was over an hour long, because each time I gave a new example, I had to show out all 4 of those properties, right? So it took a little bit of writing to kind of express all of that out. Did anybody want to ask me anything so far about what you watched in that video, or anything that I just briefly summarized here, or do people feel okay with this? We're really just getting started, so if you don't have any questions yet, it's perfectly fine. Just remember, this is a course on linear algebra, but at the same time that we're talking about vector spaces, it makes sense to include some geometry into it when we're able to make that happen. Because after all, R2 and R3, which are 2 of the most simple examples of vector spaces, have a ton of geometry in them, right? You spend so much time in calculus doing geometry, if you think about it. So it makes sense for us to try to give a notion of geometry in an arbitrary vector space. The angle between 2 matrices, or the length or norm of a polynomial, right? Or the, I don't know, the angle between 2 calculus functions. We'll talk about stuff like that. It's kind of weird. It's kind of weird. You may not be able to draw a picture of it, right? In the same way that you can draw pictures in 2- and 3-dimensional space, but you can still have this notion of sort of taking dot products from calculus and applying them now in all of these other vector spaces that we've been learning about, and trying to make some definitions out of it. That's a classic thing that a mathematician would do. And sure enough, they have done it. Let me give you another example that was not in the video of how you can use these axioms to kind of work with, or how you can practice with these axioms on a nice example. So I'm going to do a new example here, and there will be some like this in the homework, so you'll want to think about this a little bit with me. Let's assume that I have a vector v whose norm is 2. By the way, I forgot to remind you here, the norm is just the square root of the inner product of a vector with itself. That inner product of that vector with itself has to be at least 0. So you are taking the square root of a positive number here. This is not going to be an undefined thing, because the first axiom tells you that what's under that radical is not negative, right? So we do know that. So let's assume that the norm of v is 2, the norm of w is 6, and let's assume that the inner product of v and w is 3. Okay? And what I want to do here, guys, is I want to try to compute the norm of v minus 2w. Now, this is all set up very abstractly. I don't have a particular vector space in mind. I don't know whether these vectors are matrices, whether they're polynomials, whether they're functions. I don't know what they are. But all we're keeping track of here are what their norms are and what their inner product is, right? By the way, if I wanted to, I could also ask you for the angle between v and w, because if you look at the angle formula here, what do you need to know in order to calculate the angle between 2 vectors? You need to know what is their inner product with each other and what are their individual norms. So if I had given you that information up here, then you can solve for theta, basically, right? So there's multiple questions that I could ask based on what's given here. But let's see if we can solve this one. Let's try to compute this norm here. Okay, so let me show you how you would maybe work something like this out. If I want to know the norm of v minus 2w, from my definition of the norm, there's going to be a square root involved in this. Give yourself plenty of room here, guys, on this, because it's going to take a few steps. It's going to be the square root of the vector with its inner product with itself. So the inner product of V, whoops, I wrote that wrong. This should be the inner product of V minus 2W, comma, V minus 2W. Something like that, okay? And I'm just gonna keep this radical going on top of everything I'm doing. The real meat of this problem is underneath that radical right now. I have to calculate the inner product of V minus 2W with V minus 2W. Now I have these axioms, and that's what we have to use in order to work with that, right? So actually, you have an axiom 4 right there that says if you have two vectors in the first slot being added together, inner product with something else, you can split them up. And then in my video, I also explained that you can do the same thing in the second slot. Even though it's not technically an axiom to split up the second slot, you can. So in fact, guys, what you can do here is you can FOIL this out underneath that radical. You can FOIL it out. Inner product of V with V, right? Minus the inner product of V with 2W. And then minus the inner product of 2W with V. Need even a longer square root sign here. And then plus the inner product of 2W with 2W. So you totally FOIL that out, completely like so. All right, let's keep going. And stop me, you guys, if you have any questions here as we go along. This is a kind of a nice example. Does anybody want to tell me what the inner product of V with itself is going to be equal to? Be careful. The magnitude of V is the square root of the inner product of V with itself. So what would be just the inner product of V with, let me actually rewrite this one. This is the same thing as saying the inner product of V with itself would be the norm of V squared, right? If I square both sides of that equation, that's what I would have. So let me, based on that, let me ask you again, what will be the inner product of V with itself? It's 4, right? It's 2 squared. They gave us this number, which is 2. So it's just going to be 2 squared, all right? And then minus, guys, I'm going to go ahead and factor this 2 out. Now, technically, the way the third axiom works is you're only factoring your constant from the first slot. And here I have the constant in the second slot of this inner product notation. But again, remember from my video, I added the additional properties. They're not axioms, but I could prove that you can also pull constants out of the second slot. So this 2 can come out in front. I'm going to go ahead and leave the rest of it alone for this step. So there'll be inner product of V with W there. And then I have another minus 2 times the inner product of W with V. And then on this last term, I have factors of 2 that can come out of both slots, right? So 2 comes out twice, that's actually 4. And then what you're left with, guys, is the inner product of W with itself, which is the norm of W squared. Okay, so I'm just manipulating with the rules here. Edgar?
Factoring of the 2, is that 2 plus 2 or 2?
That's actually 2 times 2. That's a 2 times 2 that's coming out there. Both of these 2's get pulled out as scalars in front. And so that's a total of 4 that you've pulled out, right? And then you're left with the norm of W squared. I think now we can plug everything in. Let's see if we can work it out. The square root of 2 squared is 4. And then minus 2 times the inner product of V with W was given as 3. And then minus 2 times the inner product of W with V. They didn't give us the inner product of W and V, did they? They gave us the inner product of V with W. So what's the inner product of W with V? Is there a minus sign on that? Do we have to do anything? If we switch the order of the 2 vectors, does it matter? No. So the inner product of W and V is also 3. Okay, and then the last one is we have plus 4 times the norm of W, which was 6 squared. And now to figure this out, 36 times 4, oh geez, 144 minus 6 and minus 6, 132 plus 4. I believe that's the square root of 136. Somebody bail me out on that. Does that look right? I think so. I'm a little tired. That's the sort of thing I can't do when I'm exhausted. Can't do basic math. Yeah, I think that should be right. So that is the norm of V minus 2W. All right, everybody good on that? Nice. Okay. Question. Yeah.
When you factor out the 2 out of the 2W, comma 2W, what does it become for again?
It comes out twice, right? It actually comes out of the first slot and then again out of the second slot. It's a little different than though. I don't want you guys to think of this as like an ordered pair. These are not, we're not looking at something in R2 right here. Okay, this is a inner product notation that has certain axioms. And the axioms are if you pull a constant out of even just one slot, that constant ends up piling out in front. So if you're gonna pull that constant out of both slots, you gotta pull it out twice and pile it up twice. Yeah. So that's important to keep in mind.
Way you pull the 2 out, that's right there, right?
Absolutely. I'm using these axioms. So again, why do I like problems like this? I get to find out if my students know their axioms. So this is a good practice problem for that. Yeah. Okay. Fantastic. Well, let me take just a few minutes. I know I don't have a lot of time now, but I want to just briefly talk a little more about where we're going with the geometry of this. And then on Thursday, we will really be able to finish this up fairly quickly. So this is actually, if you're trying to keep track in the book where we're at, I'm actually going to talk now about 5.2. Most of the video was 5.1 material. And this is the stuff that won't be due until next week. So we have some time on this. But this is all about orthogonal vectors. I think the book also calls it orthogonal projections, but I'm not going to talk too much about projections in this subject. So let me talk about what it means. Does anybody know what the word orthogonal means? Yeah?
It's like 90 degrees.
90-degree angles. 90-degree angles, in other words, perpendicular. 2 vectors are orthogonal if they're perpendicular. So let's just write a definition here, though. Non-zero vectors V and W are orthogonal if their inner product is, well, it's 0. The inner product of V and W is 0. You see, that actually makes total sense when you look at the definition of an angle here. Because if you're telling me the angle should be 90 degrees, what is the cosine of 90 degrees?
So they're both on 0.
0. For some reason, I learned trig when I was, I guess I hardwired it. I have these trig angles memorized, but I realized there's a lot of numbers to keep track of. Cosine of 90 is actually 0. And so if this thing is going to equal 0, that really means that the numerator would have to be 0 in this fraction. And that's basically how we're getting the definition here. 2 vectors are orthogonal if their inner product, excuse me, is 0. Now, a lot of times we're not just going to have 2 vectors. We're going to have a whole bunch of vectors. So I'd like to give you the definition now of a whole set of vectors. I think I can put it right here in the same area of my board. Make one more definition here. A set S, which let's say it has vectors v1, v2, and ... up to vn, is orthogonal. It is an orthogonal set. All right, it is an orthogonal set if the inner product of any two of them, let's say VI and VJ, if we take the inner product of VI and VJ, we always get 0. The inner product of any two of these vectors is always 0. Let me just add whenever I does not equal J. So we wouldn't want to claim this if I was equal to J. So whenever I does not equal J, then an orthogonal set is just a bunch of vectors that are mutually perpendicular to each other. And finally, one last thing here. If in addition, the norm of the vector VI is equal to 1 for all I. So if every single vector is a unit vector, remember that from my video? A unit vector, that's just a vector of length 1. Then we call S an orthonormal set. I know I'm giving you a bunch of words here right at the end today, but these are not difficult words really. They are pretty easy to work with. And in general, chapter 5 is much more computational than chapter 4 was. It's pretty easy to tell if a set is orthogonal or not. Just calculate the inner product of any two of the vectors and make sure you're always getting 0. You'll have a formula. It might be the regular dot product. It might be some other formula, like in the video I gave you integration as a good example of an inner product. So there's lots of examples you could do. Let me just do one last example here to wrap up for today. Let's just say we took R4 for our vector space. And let's just say that S consists of the vectors, let's just say 3, 1, 5, 2. And then for the second vector, I'm just going to use 0 and 6, -2 and 2. And for the third vector, -2, 3, 3, and -6. And let's just ask, is S an orthogonal set? Now, by the way, they didn't give you the inner product formula here. I think I talked about this in the video as well. If they don't give you a formula for how to calculate inner products, then you're supposed to assume what? What is the formula I'm going to be using to check if these are orthogonal to each other? The standard dot product, right? If I don't give you a formula, then we just do the standard dot product. So let's just really quickly do it. I know I'm running on my final moments here. But if I took the inner product of V1 with V2, by the way, I'm going to label these vectors. Sorry. First vector is V1. The second vector is V2. Third vector is V3. And we can do this in no time at all. If I just want to dot the first two vectors together, right? That would be 0 plus 6 minus 10 plus 4. That adds up to 0, right? Guys, I'm checking, is every pair of vectors orthogonal? So I did V1 and V2. I also have to check V1 and V3. I'm not done until I've done all pairs. So I take the first vector and I dot it with the third vector. So that's -6 plus 3 plus 15 minus 12. Dot those vectors together, right? -6 plus 3 plus 15 minus 12, that is going to be 0. Check that one off as well. And then finally, the inner product of V2 with V3, 0 plus 18 minus 6 minus 12. Yep, that's also 0. And so the answer here is yes, because all possible pairs have an inner product of 0. So then I wanted to just ask one last thing. Sorry. Can we make this into an orthonormal set then? It's an orthogonal set, that's already yes. To be orthonormal, in addition, Every vector has to be a unit vector. Now, these are not unit vectors. They're way too big. The norm, the square root of, 3 squared plus 1 squared plus 5 squared plus 2 squared is way bigger than 1. Is there a way to turn this into an orthonormal set? Anthony? Correct. So this is not an orthonormal set, but we can get one. I'll wrap up with this. By dividing each vector by its norm. Remember that from my video, the whole normalize the vector thing? So the norm of this first vector, right? What is the norm of V1? Square root of 3 squared plus 1 squared plus 5 squared plus 2 squared, right? Whatever that is. Square root of 39, right? And the norm of V2, I'll just let you guys check these numbers. This is very easy to calculate. Square root of 44. And the third one, I believe, is the square root of 58. So how do you get this? Just really quick. You're just going to take each of your vectors, guys, and divide them by their norms. So divide the first vector by radical 39. Take the second vector and divide it by radical 44. And then take the third vector and divide it by the square root of 58. If you do that, if you just divide every vector by its norm, you turn them all into unit vectors. They're still orthogonal. You haven't changed the direction of any of your vectors, but you've made them into unit vectors by dividing by their norms. You've normalized each of those vectors. Any questions about that? That's all I've got for you for tonight, guys. Sorry, I kept you a couple minutes too long tonight, but I hope that it all made good sense. It's pretty straightforward. We'll pick this up on Thursday and try to get close to finish with chapter 5. I'll be around at 8 o'clock tonight, guys. If you want to see me in my office hours, come earlier. You might get somebody who's half awake.
Oh, yeah, those things spelling, two instead of TWO instead of.
Oh, 2 vectors. Yeah, that is me being asleep at the wheel. Yeah, thank you.
Yeah.
You know something's wrong with me if I'm doing that. Thank you.
I know, so there is one word.